Hello everyone, welcome to this week's ECE GaAs academic seminar. This week we have invited Dongheon Ha with us. Let me give you a little brief introduction for Dongheon. Dongheon was born in Korea. He got his bachelor degree in computer science and electrical engineering from Handong University in Pohang, Korea. And then he got his master degree in electrical engineering at Korea Advanced Institute of Science and Technology in Dongheon, Korea. And in the spring of 2009, he went to the Research and Development Center and at Phoenix Semiconductor. And right now he is a PhD candidate working for Professor Jeremy Mundy. His research interests include the design and the analysis of solar cells for future energy harvesting applications.
Thank you. So, hello everybody, I'm Dongheon from Professor Mundy's lab. So, today basically I'm going to talk about cellulose paper and how we can use it as an anti-diffraction layers for photovoltaics. So, basic motivation of my research is by answering the bottom question. So, can you develop a better, cheaper, and environmentally friendly anti-diffraction layers? So, here is the outline for today's talk. So I'm going to start with the talk by answering the question, why we need solar energy. After that, I'm going to introduce a traditional anti-diffraction layers. And after that, I'm going to talk about cellulose papers and how we can use it as new anti-diffraction layers. So why we need solar energy? So when you think about power generations, we can think about some kind of options, like simply we can do burning fossil fuels or do some nuclear power generations. However, those sources have critical disadvantages. So burning fossil fuels, we cannot avoid the emission of carbon dioxide, and nuclear power generations. Hopefully there are no Japanese here because that is my neighboring country, and I'm really feel sorry about the disaster in Fukushima. So you know that if the plant is not built on the safe areas, we cannot avoid disasters. So that's why people have interest in renewable energy sources. So among lots of sources, solar energy has been one of the most popular options because the sun has huge amount of energies, and solar cell is a really safe way to generate electricity. And now we don't need to worry about the emission of carbon dioxide, and we can say that, well, solar cells can provide electricity exactly when we need it. So for instance, we can think about hot sunny days in summer when we need to run the air conditioners. So, okay, we are going to use the solar energy. And to boost the efficiencies, people have used a thin film-based anti-diffraction layers. And I'm going to talk about what's the traditional method for that. So due to the nature of optics, we cannot avoid the even more than 30% of light loss at interface between air and our solar cells. So for instance, the left figure shows the reflectivity of silicon, which is one of the most popular materials for photovoltaics. And we know that throughout the whole spectrum, the reflectance is even greater than 30%. So we're going to reduce this amount. And how we can do that? So simply we can add thin film dielectric layers on top of the solar cells. And by adjusting the thickness and the refractive index of that layer, we can minimize that amount. So the bottom is the optimal conditions for that. And this figure shows the effect of the traditional anti-diffraction coatings. So red is the reflectivity of bare silicon, which is one of the most popular materials for solar cells. And that is even greater than 30%. However, when you added simple glass slide on top of the silicon material, now we know that we have less amount of reflectance. That is because now we have greater index change from air to silicon because the diffraction index of glass is somewhere else between the air and silicon. However, if we apply the optimal conditions, we know that we can further minimize the reflectance, and at the wavelength of 600 nanometer, it is around 0%. This is really good. Okay, that is good. However, there are also some disadvantages. So it is obvious that we cannot avoid wavelength-dependent behavior. And the other thing we can see here is that now we should have angle-dependent behavior because the optimal condition is valid for some specific incident angle. And one of the most critical disadvantages for this method is that we need to use very expensive and high temperature fabrication processes to make such layers. So sometimes because we need those layers require high temperature fabrication processes, they could be detrimental to some temperature sensitive solar cells. So okay, we are going to make a new anti-reflection coatings to address aforementioned shortcomings. So there are two goals for that. The first one is material goals. So okay, we're going to use an environmentally friendly, abundant, and renewable materials to make a new anti-reflection coatings. And at the same time, to make such a new anti-reflection coatings, we're going to use a simple and inexpensive fabrication processes. And performance goals is the second goal of the new ARC. So even with a simple and inexpensive fabrication processes, the performance of the new ARC should be comparable or even better than that of the traditional method. And we're going to have high transmission, large scattering, and angle independent behavior. So now I'm going to talk about cellulose fibers, and I'm going to use it as a new anti-reflection coatings. So if we really can use the cellulose fibers, which is basically paper like this, we can say that, well, because the paper is basically from trees, and now if we can really use the materials, we can say that, well, we can achieve the first goal of our new ARC because the tree is also abundant and renewable materials. So this is the actual paper that I have used, and this paper, we can see two different optical properties. One is, at the bottom of the paper, we know that this paper transmits light very well. However, at the top of the paper, at the same time, this paper scatters light very well. So we're going to use those two properties at the same time for our solar cells. So from experiment, we have shown that this paper really have large scattering and high transmission. So the left picture shows that when it shines green laser on a glass slide, and compared to the left picture, right picture shows that when it do the same thing on our transparent paper, it scatters light very well. And from experiment, we have shown that this paper has really high transmittance. It is even greater than sometimes 9%. So, okay, we are going to use this special paper as on actual anti-reflection layers on the solar cells. So these pictures shows the whole fabrication processes. So, as you can see from these pictures, the whole fabrication process is really simple. And whole processes can be conductive at room temperature. So we no longer need to use the expensive and high temperature fabrication processes if we really use it as our new anti-reflection coatings. So we actually applied this paper on our solar cells, which is planar gallium arsenide. So left counterplot shows the measured reflectivity to air from the bare gallium arsenide, and throughout the whole data point, as a function of wavelengths and the angle of incidence, we know that it is even greater than 30%. However, when we apply our transparent paper, now we know that the measured reflectivity has been reduced to around 20%. And the other thing we can see here is that even if we change the incident angle, it is around the same, which means that we have angle-independent behavior with our new ARC. That is because, as I told you before, this paper, transparent paper, has large scatterings because so that made our solar cell to have a really angle-independent behavior. So I wanted to understand the enhancement in more detailed way, so I developed a optical calculation model. So now we can assume that we have three different layers. One is air, and our ARC, which is the transparent paper, and our absorber, which is gallium arsenide. So to calculate the total reflectivity to air, we need to consider the multiple reflections, and if we consider the multiple reflections, and the total reflectivity to air can be calculated based on a geometric sequence. So if we apply that model to our measured data on the right figure, we know that for the bare cell, we know that our model estimates the measured experimental data very well. However, for the case with the cellulose paper, our model overestimates the measured data. That is because this model is just based on the difference of the refractive index. So this doesn't contain the effect from the scattering. That's why our model overestimates the reflectivity. So we understand the physical origins of the enhancement. That is the combination of the change in the refractive index and the scattering effect. So we wanted to apply this paper ARC on the other type of solar cells. One is planar silicon, and the other one is textured silicon. So on planar silicon wafer, we know that as expected, the measured reflectivity has been reduced as similar as gallium arsenide. For the textured cell, because the surface has the textured configurations, it already has even better optical properties compared to the planar type of cells. However, even on that surface, our paper ARC can further minimize the reflectance, as shown in the contour plot. Recently, people have interested in using the polymer materials for the future generation of photovoltaics. That is because it is flexible and cheap material. So we employed this paper ARC on the polymer device, which is based on P3HT. And from experiment and calculations, we have shown that this paper ARC can minimize the reflectance. Okay, so here is the last part of my today's talk. So actual performance enhancement from the using of the new type of ARC. So the first one is external corner efficiency, which is the EQE, can be defined as a fraction of number of generated electrons inside the solar cell over the number of total incident photons to the cell. So throughout the whole spectrum, EQE has been increased like 15%. And the second one is IQE, which can be defined as EQE over absorption. So because that is the solar cells, its own properties, there should be no changes regardless of the attachment of the ARC. So before the attachment and after the attachment, we have shown that the IQE, there is no change in the IQE. So finally, we determined the current voltage characteristics, and there had been around 24% enhancement in the power conversion efficiencies with the attachment of the paper ARC. So here is the conclusion for my today's talk. I have introduced a paper-based anti-reflection coatings, and that is based on a simple, scalable, and inexpensive processes. Even with a simple processes, we have achieved broad angle and wavelength operations, and finally there had been around 24% enhancement in the efficiencies. Thank you, and if you have any questions, let me know.
Now is the time for questions.
I have a question actually. It's funny because I don't think I've really asked you about this before, but how much do you know about how the paper is actually made and the processing that goes into that? Because I know most of what you've done has been the optical studies.
Mm-hmm. So, not the optical studies, what do you mean?
But how is the paper material itself manufactured or fabricated?
made the factor of the paper?
Yeah. How is the paper made?
Okay, so you're wondering about the whole paper making processes, right? Okay, so the first one is, okay, let me go back to the previous slide. So this schematic, the pictures and schematic is from the previous paper of mine, from the nanoletters. So to make these papers, first we needed to change the concentration of the cellulose fibers. And we can adjust the concentrations by changing the fraction of the waters and the cellulose fibers. And if we pick some proper thickness and the length of the cellulose fibers within a solutions, so paper making technique is very simple. It was originally in the solution material, and we can simply dry it, and we can achieve the cellulose fibers. And the other thing we have to consider is, because we want to use the really pretty simple paper, and that shouldn't be thinner than the 40 micron, because the fiber, the thickness is 40 micron. But if there is like double layers, so triple layers of the fibers, is going to be thicker. So we don't want to do that. So for this, first we need to, okay, the first thing is we need to keep the proper concentrations, and the drying process is, there is some kind of special techniques for the dryings, like we need to use some heaters and some kind of rollers, something like that. So if we do the whole things, we can make a single layer of the cellulose fibers. Yeah.
I also have a question. Because you use paper as the anti-reflection coating on the surface of the solar cell, how do you make sure that this paper will stick to the surface of the solar cell? Okay,
that's really good question. So actually the attachment process is really tough at the initial of my research, because okay, I have the paper, I have the solar cell, I need to attach it, right? But I actually had hard time to attach the papers on actual solar cells, because if we have some like air gaps, what you want to do is gradually index change from the air to the solar cells, because the refractive index of the paper is somewhere between those two. However, if we have some air gaps, that's going to break the whole thing. So first, I have used the simple Scotch tape, and sometimes I use the waters. However, those things didn't work. So I actually found some literatures and found that polyvinyl alcohol can attach the cellulose fibers to the some kind of semiconductors. Because also we can use that chemical, because the refractive index is exactly the same as the cellulose fibers. It's lucky. So it's around 1.5. So it didn't break the gradual index changes, and that they can hold the papers on the solar cells very well. So yeah, I have used the PVA.
Is there any thickness dependence of the paper? I mean, if you thinner is there or thicker is there, something like that?
Yeah, that's a really good and tough question. So yes, there should be, but for my research, because the when I was answering to Dan, I told you that the thickness is 40 microns. So it's already pretty thick compared to the scale of the wavelengths. So we don't need to consider about the coherent behavior of the wavelengths. So because it is pretty thick, so the surface is pretty low, so we cannot expect the kind of coherence in the phase shift of the wavelengths. So that's why I didn't say anything about the phase effect of the when I was talking about my optical model. That's because I can calculate the estimated reflectivity just based on the change of the refractive index. However, as you pointed out, if the thickness is really thick, like even less than 1 micron, or somewhere else, compared to the wavelengths, definitely we need to consider the effect of the phase shift or something like that. So that is true, but for my research, actually that's not critical.
Okay, so let's take our speaker.